So in part two of this discussion about fragmentation, I'm going to try to use some simulations that demonstrate how reserves can help us establish resilience for harvest. And this might be something like having a harvest area where, say, pigs are harvested in a rangeland, but then they also have a reserve where they're not hunted, just for example. And the first thing I'm going to go through several progressively more complicated models until finally we get up to the point of adding a reserve and how well that reserve might be able to balance the population. So the first model that I'm going to use is just a model that shows the growth of new pigs with carrying capacity. And if we run this model, this in red here is the number of new pigs coming into the population. In blue is the population number going up toward the carrying capacity. And this number down here below is the growth rate. And as the population increases, the growth rate decreases. And that's because it's decreasing down to 0 as the population goes to the carrying capacity. So if we watch this simulation with time, you see that there's this peak of new pigs coming in at about half of the carrying capacity. And this is where you'd have your maximum yield. If you were to just harvest at this rate, you would get the most pigs out of this system. So again, this is very simplified. We wouldn't use a model this simple to actually manage a population of pigs. But the idea is at low populations, maybe a rapid growth rate, but there's not very many pigs to reproduce. Get up to sort of an intermediate level of pigs reproducing. They haven't started to slow down their reproduction rate because as they approach the carrying capacity, they're still away from the carrying capacity, and they end up producing a large amount of new pigs. And this maximum sustainable yield type idea is used in fisheries and other sorts of management. So what I want to show is go to the next step and throw in a little wrinkle on top of that, which is going to be that we're going to have the harvest. We're going to harvest at that carrying capacity. So in this case, I've got a population growing. I'm just going to run it to often these simulations need to be run just for a second to get them to auto range. So I'm going to run it, and we can watch this blue is the population, the pink or magenta here is the new animals, and this curve down below is the growth rate. You see it's getting up high as the population increases. Now it's dropping down. And this simulation is set up so that I can adjust this slider and actually harvest part of the population. And that harvest is going to be accumulated harvest is going to show up in red. So again, I'm just going to stop it because it needs to auto range. If we see this population just as a logistic growth curve goes up here and levels off at 1,000. So what I want to do is start harvesting when the population gets to about 500, and I want to keep the harvest at that level to get my maximum accumulated harvest over a period of time. And that accumulated harvest is also shown up in this little blue box, but that might not show up too well in your version of the video. So if we run it again in this interactive mode, I can increase the harvest just by moving this slider. So again, I'm waiting, the population is a little low, but now as I get there, I can take I harvest out, and you see I'm slowing down the growth rate. If I harvest a little bit more, population drops. If I harvest a little less, population goes back up. So I can adjust my harvest rate and get an adjustment on the overall accumulated harvest and over this period of time. I can just leave it at this harvest rate. It's just going to level off, and then after so many time steps the simulation stops, and it's going to show me what my accumulated harvest was over that whole period of time. Okay, this is one strategy. Now you see it looks pretty busy here, but look at this red line. It's just the accumulated harvest goes up more and more as we just left it at a particular harvest rate over this time scale, just accumulating more and more harvest. Okay, now what if there's variations in the environment? And this is what I'm going to look at next. What if this carrying capacity, instead of being constant, actually fluctuates around, say, because of seasons, or maybe there's a bad year or something like that. So I'm going to open up another simulation that has variation in the carrying capacity. So instead of the carrying capacity being a constant over a period of time, it is the carrying capacity varies because of the say seasons or maybe some other factor. Now what I'm doing in this model is I'm just letting it run a little bit again so that I can have it be auto range. Stop. Okay, so you can see that the number of new animals is sort of jumping around a little bit here, and that's because there's a variation on like a daily level on the carrying capacity and a variation on a longer level on the carrying capacity. All right, so now if I run this for a period of time, I can harvest, and I could set up a rule. I could make up a rule that whenever the population gets above a certain amount, I could increase my harvest and decrease the population back to, say, I could try to keep the population around 500. But you see I'm always having to adjust. There's some underlying variability, which I'm not showing you in this graph, but there's underlying variability even if I have a fixed harvest rate, I get this variability. And if I harvest too much, I could cause a collapse in that population, and then would I really be able to recover? So this ends up being a very sort of complicated set of rules if I was going to try to say, well, I'm going to use the harvest rate to really chase that variation in the carrying capacity. So here what you see over the period of this time, the pink is the new animals that were coming in. The blue is the population, and it varied around, and when it's a little different, I mean this is hard to see on this busy graph, but if you remember when I was running this, I was changing the harvest proportion in order to try to chase that changing carrying capacity. Okay, so that's one way you might try to manage a population. Now another way is to set up a reserve, and all of the organisms, like in this case we're talking about the mythical pigs that live up in the forest, we're going to have a variation in the carrying capacity just like we saw before, but what we're going to allow for is we're going to allow a certain amount of that population to come in from a reserve or a refuge. So here we have our working population, and the carrying capacity and the growth rates are the same in the refuge as they are in the working population. And I can set this whether I allow animals to come in from the refuge or the reserve. If I set it to 0, there's no immigration. If I set it to 1, it allows that immigration, and if there's less animals here than there are here, then some animals flow through. And then I can also set like a maximum harvest rate. So we're going to run this a few times as I talk through this, and it's first set so there's nothing coming out of the refuge. And I'm going to set the maximum harvest rate here at just 25%. And as we run that, so it sets the maximum harvest rate, and what you can see is that the refuge population here is in red. It goes up and just stays up. The working population is blue, and as the carrying capacity, or the reproductive capacity of the whole thing goes down, it drops, and then we have this little period in here where the growth rate is really zero, that there's a bad section of the year. And so if we keep on a continual harvest rate, we drop that population, this little drop right here, and there's nothing to replenish it, and it could be a severe drop. Now if we go up to, say, change the harvest rate up to 40% and run it again, we see that in that little window when the population was really starved and not doing very well, there was a bigger drop. And finally, let's just jump right up to 80, harvest rate of 80%, and run it. And we see at that level, that amount of harvest that we took was just too much, and it caused the population to collapse. All right, so we could refine these maximum harvest rates in here, but the point of this illustration is to go back and say, well, what if we allow immigration from the refuge population? So we turn on the ability of the refuge population to fill that in, and if we look at, say, something like 25% harvest rate and run it, really don't see much different, because there's a lot of animals there, but even the normal harvest rate isn't having that big of an impact on the population. It's a little flow from the population. Oops. Okay, we go up to 50% like we did before. We run it. We see that in this case the population started dropping down in the working population, and you see that the refuge population also dropped in order to fill that in. And finally, just for illustration, go up to 80% of a maximum harvest rate, set it at 80 and run it. What we see is, as that population went down, the refuge really contributed a big chunk of new animals, and that population was fairly well stabilized. So the simulation on the reserve and the working population showed logistic growth rate. We were looking for maximum sustainable yield. And if we try to increase the harvest, even in times of variability, we could use rules, but that would be very sort of complicated. We're always sort of chasing the conditions. But instead, if we thought, well, let's build in some resilience. We've got a refuge here with our population. Build in this connection. It allowed for a high level of harvest, and even under some extreme conditions that would lead to population crashes without the refuge, it was able to cover that. So this is a good example of how managing these natural resources and essentially hardwiring in a refuge or a buffer allows us to actually get more out of the ecosystem for human use. Okay, now I'm going to switch gears here a little bit and talk about how these reserves in urban areas, corridors and reserves, natural areas, green spaces, all those things are like islands. And here's a diagram of what we mean by this is island biogeography theory that you're going to read about. And then if we have the mainland with lots of animals on it, and there's a big large island nearby, it has a large number of species. Small island that's sort of near, it's going to have many fewer species. And a small island that's small, it's going to have very few species. And this is because there's a immigration that comes in off the from the mainland to the island, and then there's a natural level of species extinction that just takes place on any island because of bad luck or overpredation, something like that. So an island that's large and close gets a lot of immigration and has less localized extinction. An island that's small and far has both not so much immigration because the animals have to get all the way over there, but they also have higher level of extinction, so they end up with this much lower population. So this is a general trend, but one of the ways you can think about it is, what if you have a big forest park or a big ex-urban natural reserve, and you have all these parks within the city? If they're large and close to there, they could have like a lot of biodiversity, but if they're just small and isolated, they're going to have very little biodiversity. They need to be connected. And we can talk about this in terms of the number of species that come in, not numbers of animals, but species. Like immigration depends on how far they are from the main reserve, the main source of species that replenishes that. And then also the loss of species. The smaller the island is, the higher the loss of the species. So this is really sort of a generalized trend, but you can use it to look at why it's important to have many small reserves right next to each other, and then have those connected to some sort of large source that replenishes that biodiversity continually. Okay, the last topic for today is to talk about really what type of landscape pattern do we want to see for highest biodiversity. And really one of the best types of patterns is this mosaic pattern. We talked about this in the first in lecture 2 when we were talking about patterns. And if you imagine this as a forest, there's areas that are just being burned, there's areas that are recovering from being burned, there's areas that are clear because nothing has grown yet, and then they grow up into bigger trees. And so instead of thinking about succession like we had last week, where we had bare land going to some sorts of trees, going to the climax forest, this is a continual set of successions that are being interrupted all the time by small disturbances. So eventually a little patch will end up with the same trees as the climax forest, but all along the way then it gets reset, or maybe there's a fire or landslide or something like that, windstorm, gets reset, and you end up with, across the landscape, a wide range of ages, of different forest ages, which then means they're all different plant types and different structure. And these are all connected, so animals can graze in multiple different age categories. They might be eating berries sometime in a very young age of a succession, and they might be up in the trees in a very old age of a succession. So they use all these different habitats that are in this mosaic. So it's very good for maintaining biodiversity. And one of the questions I'm going to have you be thinking about this week is, how is this sort of mosaic different than fragmentation? I mean, there's not one big forest with all the same type of trees. There's a whole bunch of patches that all have different ages. And how's that different than fragmentation? And then what does that mean for how we think about managing these resources? So, just to sum it up, humans cause fragmentation through our activities. Fragmentation is a big threat to biodiversity. So understanding the desired level of connectedness and how connectedness works in habitats helps us, and we use the network view to do that. And having reserves that are connected by corridors can be valuable for biodiversity, and it can be valuable for, if we're humans, we're trying to take some resource and harvest it for our economic purposes. It's useful for that. And then finally, this mosaic is thinking about a mosaic on the landscape as a highly dynamic pattern where it's not all just one connected set of the homogeneous habitat, but all different types of ages and types. It's very good for biodiversity. And how can we try to get to that sort of pattern to promote biodiversity?